So welcome to today's coffee lecture of the Chemistry, Biology and Pharmacy Information Center here at ETH Zurich. My name is Leo Betschart. I'm an organic chemist by training, and today I will give you a quick overview over Synthia, a new tool we have available here at ETH. So first of all, what is Synthia and what can you do with it? It's an online tool that helps you in planning multi-step organic synthesis and discover new option or also explore different suggestions. We have just recently started licensing it, and by the time that you see this video online, you certainly will be able to register for the software and start using it. And you can see the information in the show notes below. But now let's quickly have a look at the history of Synthia. Coming back to the title page with the spider web, how did this come about? So there is quite a bit of research behind this, and this started in the research group of Bartosz Grzybowski, which was at Northwestern University, and then moved to South Korea, and did a lot about networks of compounds and reaction networks. So this is a paper from 2012, and they initially developed this software under the name Chematica, and it was then at some point bought by Merck and rebranded. And maybe the difference, because if you are a synthetic chemist and interested in synthesis planning, you probably have either worked with SciFinder or Reaxys. They have synthesis planning tools too, and those are based basically on the reactions that are within their database. Synthia is different, that here rules for chemical reactivity are encoded into the software. So there is a bunch of chemists in the background that create these chemical reasoning rules. And so here you will get slightly different results. If there are steps that are literature known, they will also be presented with literature. So why would you use this? Well, it can assist in your synthesis planning. There is different algorithms that you can use. So for example, a FAST that gives you quick and dirty predictions of how you might go about the synthesis project. They have an algorithm that is optimized for heterocyclic compounds. So that is more relevant, for example, if you're into medicinal chemistry, but also if you are in material scientists, you work with optical sensors where you have large pi systems, then of course you have a lot of heterocycles. There is also an algorithm for complex molecules. This doesn't work so well. And I think it's also represented in the literature when you see how much work that goes into synthesizing large complex molecules, and that there is a lot of unexpected chemistry going on where you have to find workarounds. That's something that's not easy to predict. The thing that you can then do is explore the paths that are given to you in different visual ways. And then finally, also a feature that I want to highlight is the shared path library. So you could say, I want to make these, and these closely related compounds, and it tries to sort of give you a common pathway that you have something that you don't need many different precursor, but can use one and then at some late stage point diverge into what you actually want. So maybe now I go live to show you what this looks like. So once you log in, you see syntheses that you have run in the past. So there are a bunch of these. And now I quickly just copy one of these molecules and say I want to start a new analysis. And I've had some technical problems, so I'm very happy that I have these older molecules that I've already run, so I can show you something. So here, for example, if I have drawn a molecule in ChemDraw, I can copy it as a SMILES and then simply paste it here with Control V. I hope this works. No? Oh yeah. So here I have, of course, some binap derivative, and then I can choose some of my algorithms, and that's where I have the problems today, because now this is grayed out and I don't know why, so I cannot really start the search. But here I can basically choose my base algorithm, and then I have a lot of options that I can use to fine tune. So let's quickly look at what these are or might be. So under this tab, analysis preference, I can, for example, include things like robust reactions, or if I don't want to work with any gases because maybe I'm not equipped in my lab, I can exclude such things. Or if I want to be metal free. So these are all things that I can specify beforehand. I can also say, well, this needs to be short, or I don't care about the number of steps. Of course, no synthetic chemist wants to do unlimited steps. If you maybe don't care about stereochemistry, you can also exclude stereoselective reactions, and then you get more general transformations, and so on. So there's a lot that you can specify here. Then you can also sort of focus the search more. So if you know automatically there are obvious disconnections that you have already thought about, you could exclude these, because then the algorithm focus on other stuff. Or you could also say, well, I want to focus on a certain pathway and find more suggestions around that. So you could put that into the seek part here. And you can also do that with smiles. You can also use CAS numbers. So if you want to exclude certain starting materials, you can also use that here very specifically. And then finally, there is starting materials. And here, of course, it's about accessibility, about what it costs per gram or per mole, and also availability. So if, for example, the availability is under a gram, you can exclude that. So these are some of the things that we can do here in the configuration. And then you run this, and then that takes some time. So it could be for an easy molecule that within 10 minutes you have a result. Typically after half an hour, I would say it's finished, and you just start this, you can log out and it runs on this server. If you have a complex molecule, it can take several hours, especially if you specify, oh yeah, you want to have 10,000 iterations done, and that might be necessary if you have high complexity. Then let's say we have run the analysis. So now we want to see what the results look like. So let me quickly move here to the second page where I have this very simple example that we could look at. And there is several views that we could use. One is simply, and that's actually not the one that I want to start with. So here, the starting material view, where I just see, oh yeah, this is my target, and these are the building blocks where it's traced back. I can sort these according to a ranking. So that is a mixture of the criteria that you entered in the beginning, where you put the focus. I can sort by number of steps, also protecting group manipulations, and then similarity to chemical literature or to the chemical rules in the background. But if I want to actually see what's being done, I can change this here and then look at the actual pathway. And then it looks like this. So I have two starting materials and a transformation, and we can zoom in a little bit. And then we see here there is a literature reference. I can click on that and get some details. And then I have representative papers for this transformation where I can read up on it. But this is not comprehensive. This is selective. So if you think, oh yeah, this could be interesting, maybe you want to more thoroughly search on it. So this is not Reaxys and not SciFinder. It's not the goal of this tool. And you see there's 2 stars here. If there are 3, then it's a published reaction. If there are 2, then it's something that's deemed by the algorithm to be have high confidence. If it's only 1, there is low confidence, and sometimes there are just steps suggested by chemical intuition that have no literature basis that is associated with it. And then we've initially seen the graphs. That brings me back to the spider web I showed you in the beginning. So here you could also visually explore a little bit and you do mouse over, and then you see certain intermediates, and you see also where are the pathways very linear, where is the branching late in the synthesis, or where is it very early on. And maybe for that, I want to show one last example that I just tried before with this highly complex molecule, where I was astonished that I got even some results. So here I had to run the algorithm several times and do many iterations to get anything at all. I'm also, it's not all that promising. And you see here now, you have a complex network. You have starting points that sort of go together from different places that you could go to the same intermediates. And again, here we see in blue, so there's a color coding system that you could look up with the legend. So that's what this software does. And with that, I think I'm coming to the summary of what I wanted to say. Oh no, didn't work. So we have many options to tailor the search with Synthia. We can sort the result. We can visually explore them. There are references to relevant literature. They're not always there, but as much as possible. It's a rule-based system, so that makes it distinct from others that are hardcore machine learning, where you have implicit rules that are extracted from a large amount of data. You, of course, need an investment of time to set this up, maybe also to get a feeling what are all the buttons you can push to get the result you want. For complex molecules, I'm not convinced that this always works well. So with the one that just that I shown last, there was an example where there was an aldehyde in the molecule, but they actually then did an organometallic addition of an acetylide to an ester functionality that's also in the molecule, and expected it to react there mainly and leave the aldehyde completely intact. That's something I don't deem likely. So I think with the rules, you still need some chemical intuition to judge, oh yeah, what is now reasonable, what would make sense for me. It takes time also to run, not only to learn. And with that, I'm at the end. I have a little summary here that you can download as a digital coffee lecture card, and I should quickly pop this in the chat so you can also download it, those who join digitally. And if you have any questions, I'm happy if you unmute or if you just ask if you're here physically. Yeah. I haven't seen one yet. For us, so the question in the audience was if there are performance analyses, how these compare the two systems. I haven't seen any. That doesn't say that there aren't any. What I think in some respects, the results are also comparable. From my impression, what I like about Synthia compared to the SciFinder and Reaxys tools is that here you have much more control over what you do, and I think it's also easier to explore. And I would also say that some of the analogies work better because they are sort of chemical intuition encoded. And what I, for example, often see in these machine learning tools is that there are strange or unusual analogies are taken. So, for example, every chemist knows that if you have a benzylic or an allylic system, this will quite react differently than if you have a saturated system because it's electronically activated. And the machine learning tools, they often sort of regard these as equal. They just see, oh yeah, it's the same group, so it must have the same activity. And then when you then look at the literature that's given as precedent, then you see, well, but this is at least electronically very different, and it's not gonna work out. And I feel I've seen this less here, but yeah, I haven't quantified.